Welcome, and thank you for being here and listening to our talk. Thank you NSF, DOE, and ARM for your generous support to fund this work, allowing us to spend 6 years on this project. We appreciate it. I'm Simone Campanoni, an author of the NOELLE Compiler Research Accelerator. NOELLE has been designed and developed as a collaboration between my Arcana Compiler Research Group and Professor David August's group, Liberty. Together, we are the Parakinetics Group. We started NOELLE in 2016 to accelerate doing compiler research in our groups. In other words, we are the first users of NOELLE. We designed NOELLE and developed it while doing research that relied on it on a variety of compiler and optimization topics. If you are interested, please take a look at what we built upon NOELLE over the years by following the link below. That will lead you to this page. NOELLE grew over the years, supporting more and more abstractions that we relied on to accelerate our research. We decided to open source NOELLE with the hope it will be useful to others as it was, and still is, and will be, to us. This work has been done over the last 6 years from many people, including undergraduate students, master students, and PhD students. I would like to thank everyone involved, especially Angelo, which he was the first student to work on NOELLE, and he kept working on it for years, even after he completed his undergraduate studies. It was a true pleasure working with them, and with all other authors of the NOELLE paper, of course. So, why do we need NOELLE? Technology scaling ended, and therefore there is no free lunch anymore. However, the demand of more computational power and energy efficiency keeps growing. Somehow, we, as community, need to fulfill such need, which created the beginning of the golden age for both computer architecture and compilers. If you have not done already, please watch the related fantastic and inspiring talks from David Patterson and Chris Lattner. Our focus is on the compiler end of this revolution. Compilers are useful to translate source code into binaries while optimizing the code. They are also useful to unlock the power of new architectures or hardware features. So either to further optimize the code or to unlock the hardware potential, compilers constantly evolve. Our group mostly focuses on innovating compiler optimizations. So let's dive into compilers optimizations. For decades, compilers have been designed with a front end that translates source code into an intermediate representation IR, a middle end rich of code analysis and transformations that aim to optimize the program, and a back end that translates the resulting optimized IR into machine code. Our research agenda mostly targets the middle end, where most optimizations happen. So let's dive in within the middle end. The middle end is composed by many code transformations. Such transformations can be grouped in 3 categories. First, there are the simplest transformations which rely on concepts that are explicit into the IR. Hence, these transformations do not need any code analysis to run. For example, the transformation that merges multiple consecutive busy blocks, which is already available in LLVM, relies only on the concepts of busy block, its successors, predecessors, branch instruction terminator, which is the last instruction of the busy block. All these concepts are explicit into the IR, so the code transformation simply uses them. The second group of transformations need to rely on concepts that are not explicit into the IR, so they need code analysis to capture them. These transformations query directly a code analysis on demand, so only when the information is needed. Finally, there is the last group, which includes the most advanced code transformations. Such transformations are designed differently. Many code analyses now are used to generate one or multiple abstractions that capture properties of the code being optimized. Such abstraction or abstractions are then used by all code transformations that need to rely on the existence of, or lack of, these code properties. Complexity of transformations of this group varies significantly, ranging from a relatively simple one called loop invariant code motion, which hoists instructions outside loops whenever it's safe to do so, to significantly more challenging transformations like automatic code parallelization. I believe that one of the biggest roadblocks for the compiler community to create innovation in code optimizations, which is essential for the compiler's golden age, is having the right abstractions that are used by this third category of code transformations. This comes from a personal experience. And you might have found yourself in this situation as well, where I was designing a new code optimization, and instead of spending most of my time implementing it, I spent the majority of my time designing several ad hoc code analyses from scratch to overcome the lack of proper abstractions that were available in the middle end. The result was a code base where most of my code was spent in ad hoc code analysis, which could have been eliminated by having a few extra abstractions in the middle end. Not only this slowed me down in pursuing our research agenda, but also led to hard to maintain code, hard to share code analysis between research projects, and a much higher bar for new people to join our research project because they had to understand all of these ad hoc code analysis. So let's look at an example of abstraction that is currently used by code transformations. Let's imagine that a code transformation needs to move a store instruction before a load. Such transformation needs to know whether this is safe to do so or not. Instead of creating an ad hoc code analysis, we can use the alias abstraction in LLVM. With this abstraction, we can check whether the two pointers P and Q that the load and store instructions use can point to the same memory location or not. If they don't alias, therefore they cannot point to the same memory location, then our code transformation can swap the two instructions. Otherwise, it cannot. Notice that this abstraction alias is not explicit into the IR, but it is the result of running code analysis, alias analysis in this case. While having this alias abstraction is already a great starting point that accelerates some code transformations, especially the ones in the left side of the complexity spectrum, we argue that this needs to be only the beginning. The few abstractions available in LLVM are a great start, but they are still too low level, which currently creates challenges for the more complex transformations. This is why we created NOELLE. NOELLE is designed to complement LLVM by providing high-level abstractions that we know are important for advanced code transformations like parallelization, vectorizations, etc. NOELLE is designed following LLVM principles, including being implemented as a set of libraries that you can take and put together in the way you want, which enables you to implement your specific IR code optimization pipeline with ease. In our group, when we want to implement a new optimization, most of our time is now spent designing and implementing the optimization itself, rather than building ad hoc analyses and ad hoc scripts to create an optimization pipeline. This is because we rewire NOELLE for the research project-specific needs. And we tested this versatility of NOELLE on many and significantly diverse research projects. Abstractions that NOELLE provides range between just a little higher level than what LLVM already provides, like a dependence graph, where you can check dependencies and their properties between arbitrary pairs of instructions of a program, to much higher level abstraction, like the concept of reduction. Most of these abstractions are known by the research community, but are not yet available or open sourced. We invested 6 years implementing them robustly, and we made a few extensions on these abstractions to fulfill the modern needs of code transformations. And we made them available to the research community with the goal to accelerate innovation in compilers. More broadly, NOELLE relies on the observation that having high-level abstractions enable robust implementations of advanced code optimizations that are currently obtained only in ad hoc and fragile prototypes, sharing complex code analysis between advanced code optimizations, significantly reducing code complexity and maintenance costs between advanced code optimizations. Maintenance cost is a problem for everyone, but in academia is particularly painful. We don't have a lot of resources, and our goal is to innovate. So it might be a little counterintuitive, but maintenance cost of our research prototypes that we build upon for creating more and more innovation is holding us down. So we are particularly sensitive about this cost, and NOELLE has helped us tremendously. We hope it will help you as well. NOELLE includes not only abstractions. So let's look at NOELLE structure so you can see how you can use it. NOELLE includes several code abstractions powered by many domain-independent code analyses. NOELLE builds upon LLVM, and it analyzes and transforms the LLVM IR. NOELLE is designed to augment LLVM without masking it. In other words, An LLVM middle-end pass can use both NOELLE abstractions and APIs as well as LLVM ones at the same time. So the designer can choose when to use NOELLE and benefits from high-level abstractions and when instead use low-level ones. When a middle-end pass invokes NOELLE to access a high-level abstraction, NOELLE automatically decides what to run to fulfill that needs. If a given abstraction hasn't already been created, then NOELLE invokes the necessary code analysis that collectively power the requested abstraction. When the abstraction is ready, it is returned to the middle-end pass that asked for it. On top of abstractions, NOELLE also provides high-level code transformations that an optimization can rely on. Such code transformations are designed to rely on NOELLE's high-level abstractions to provide their higher-level APIs. For example, extracting a set of instructions from a loop that depend on each other, forming a strongly connected component in the dependence graph to place it to an external task that can run in parallel, can be implemented in a few API calls with NOELLE. On the other hand, if you try to accomplish the same result using low-level abstractions, it will take you many thousands lines of code. And I know it because I did it, unfortunately. Powered by these high-level abstractions and code transformations APIs, we built 11 advanced code transformations to cover the complexity spectrum, ranging from our implementation of the loop invariant code motion, which is significantly smaller and more powerful than the one available in LLVM that relies on low-level abstraction, to several advanced automatic code parallelizers. Finally, NOELLE provides a range of tools to help you building your customized optimization pipeline. For example, if you want to invoke an optimization until a fixed point is reached, then you can invoke NOELLE's tool specifying only which optimization to run. The tool itself will take care to implement the fixed point semantics for you. So now let's dive into NOELLE abstractions. NOELLE includes abstractions that are either not available in LLVM or they extend the LLVM ones in terms of richness of their description. Let's look at an example. NOELLE provides a strongly connected component direct acyclic graph abstraction of the dependencies of a loop. This abstraction simplifies the task of an optimization to understand the groups of instructions that depend on each other in a loop. This can be used, for example, to parallelize the code or to vectorize it. NOELLE SCCDAG extends slightly the one described in literature. The extension was necessary because the design goal of NOELLE is to provide abstractions and APIs for different code granularities. So optimizations built upon it can choose the granularity that better fits their needs. Because of this, NOELLE's SCCDAG is a hierarchical graph where the hierarchy is for both nodes and edges. At the top of the hierarchy, we have nodes that represent either an SCC of a dependence graph of a loop or single instructions. Nodes can be internal or external. Internal nodes represent computation performed within a loop. External nodes represent computation outside the loop that either feeds data to the loop or consumes data generated by such loop. For example, instructions that compute live-in variables of a loop are a subset of the external nodes. Each SCC node can be inspected to look at what is composed of by going through its hierarchy of nodes. In this case, this SCC is composed by two instructions, and you can see why this is an SCC. There is a cycle of dependencies between the two instructions. You can inspect in this way any SCC that composes the SCCDAG. You can also traverse the SCCDAG at the lowest level of the hierarchy going across SCC areas. This is important because sometimes you need to know how the data flows across SCCs at the instruction granularity. Finally, each node at any level of the hierarchy includes information about its properties, like whether its computation can access memory, whether dynamic instances of that node can commute, their memory footprints, etc. Notice that this abstraction does not optimize the code in any way. It simply describes the code using different lens. It is the optimization that relies on this abstraction that decides how to use this information to optimize the code. Also, this abstraction is not explicit into the IR. To compute it, NOELLE had to run several complex code analyses, including more than 20 alias analyses and many specialized data flow analyses. NOELLE's SCCDAG abstraction exposes a hierarchy also on edges, not just on nodes. From an edge at the highest level of the hierarchy, like the black one highlighted here, you can dive into it to understand why this edge exists. The hierarchy exposes the instruction level dependencies that led to this higher level edge. For example, in this case, There is a dependence between the two strongly connected components because of two instruction level dependencies, one from instruction I to J and another dependence from instruction I to K. Finally, each edge describes properties of the dependence it models. NOELLE provides APIs to transform the code at the same level of these abstractions. For example, you can move strongly connected components, schedule them around the loop or outside. And this is just an example of an abstraction and related API that NOELLE provides. NOELLE provides many more, and please look at the paper for their description. Examples of other abstractions are the program dependence graph, reduction, the environment of a code region, which is the live in and live out of a code region, a data flow engine to quickly implement new and specialized data flow analysis, and others. NOELLE provides also APIs that rely on the abstractions previously mentioned to implement code transformations like a domain-independent scheduler framework where you can easily implement your own code scheduler, and many more. All of these abstractions are powered by many advanced code analyses that directly rely on LLVM low-level APIs. NOELLE also provides tools to help you building your own optimization pipeline. Powered by NOELLE, we built several advanced code optimizations, including Helix, a parallelizing compiler that myself and my collaborators have previously spent 5 years of our life building without using NOELLE. We built Helix in a few months with NOELLE. We also built DSWP, another parallelizing transformation that was proposed by Professor David August's group. So now, with just a few months of developments that heavily rely on NOELLE, we built the first compiler that has both DSWP and Helix under the same umbrella. Not only we did this in just a few months, but our implementation of these code parallelization techniques is so robust that we tested on more than 90 benchmarks from the well-established benchmark suites, SpecCPU 2017, Parsec, MiBench, and Polybench. We also built the compiler and optimizer for Karat, a co-design between compiler, operating system, and architecture to replace memory paging without any hardware support. We built many more, including our own implementation of the loop invariant code motion, which is much smaller and more powerful than the one included in LLVM. While these optimizers were all built using NOELLE, it's important to understand how much code reuse was enabled by NOELLE. So to this end, we can look at each NOELLE abstraction and how many optimizers have actually relied on it. As you can see, each NOELLE abstraction was used by many optimizers, including the SEC DAG one. Loop-oriented abstractions had the widest adoption. A nice side effect we noticed with NOELLE and its modular design is that it helped students specializing on the aspects they care the most, making them much more productive. Some students were more interested in enhancing NOELLE, while others were more interested in building new optimizations upon it. Both goals are important and we need brilliant minds for both of them. This specialization allowed us to include many advanced code analyses that further power NOELLE's abstractions. To give you an idea of an empirical impact of enabling people specializing on one of the two aspects of optimizations, let us consider 100% to be the total number of all possible memory dependencies of a program. And let's study a given benchmark, FracMine from the Parsec suite. If we use only LS analysis of LLVM to build the PDG abstraction, as it was at the beginning of NOELLE's timeline, then we'd obtain that most memory instructions depend on most of the other memory instructions. In other words, a memory instruction is likely to depend on all other memory instructions. Arguably, these abstractions, even if it is at a high level, is not that useful in practice. However, after adding many external alias analyses, including SCAF and SVF, that can now collaborate using NOELLE's central engine, we have reduced the dependencies down to 40% roughly. Of course, we didn't just study FracMine, and this result holds on all benchmarks we studied. So please look at the paper for details. NOELLE started in 2016, and over the years we built more and more abstractions. Recently, we focused on improving their accuracy, and we obtained significant gains in most abstractions. NOELLE is an ongoing project. It's not going to end with this publication. This is because ourselves are users of this technology and we needed to keep innovating in the compiler space. So heads up that new abstractions are coming into NOELLE soon. NOELLE is open sourced on GitHub. And to have an idea about how active this project is, take a look at my GitHub activity, which is mostly composed of my development in NOELLE. Finally, NOELLE is designed for both research and education. My advanced compiler class that I teach at Northwestern is designed around NOELLE, so I share tutorial materials of this class website. So if you're interested in trying NOELLE, please start there. To conclude, we designed NOELLE to accelerate research in the middle end, which will impact compilers as a whole. The computer architecture community can also benefit from by adapting optimizations to enable new hardware features or brand new whole architectures. I would like to thank you all for listening how we spent 6 years of our life. I hope NOELLE will help you innovating in the compiler space as well.